Welcome back, and in this next video we're going to be looking at some of the ways we can measure the rate of a reaction. So you need to know and understand and be able to describe all the different methods that you could use, and we're going to be looking at those on the next couple of pages. So you're going to need your notes and the textbook for this next part. So we're on page 10 of your notes and we're looking at the reaction between calcium carbonate and hydrochloric acid. So if we write an equation for this, I've got calcium carbonate, CaCO3, solid, and hydrochloric acid, HCl, aqueous, and they react to form calcium chloride, CaCl2, that's going to be aqueous, and water, so liquid, and carbon dioxide, which is a gas. To balance it up, I'm going to put my 2 in front of there to get to HCl. Now there are 2 ways I can measure this reaction. I can measure the volume of gas being given off, or I can look at the change in mass as that gas is escaping. So those are the 2 methods that you need to be familiar with, and you need to be able to draw and label the equipment that you would use for this type of measurement. So for this type of measurement you could use look at the volume of gas being collected. So we can either have this set up where we have a syringe to add our hydrochloric acid, or a flask containing the marble chips and the hydrochloric acid sitting underneath them. This is then connected up to a gas syringe which will measure the volume of gas produced. The alternative method for this would be a flask, again with the hydrochloric acid and our marble chips, and this time we're bubbling it and collecting it either in a measuring cylinder or better in a burette. And you saw that a long time ago when we did magnesium in acid to release hydrogen gas. The other method I could use is basically the loss of mass. So we start with our acid and our marble chips. We add our marble chips and then we watch the mass going down as the carbon dioxide escapes. Now the measurements you need to take are always going to involve time, because it goes back to the idea that we talked about previously, that rate is equal to the change in concentration over the change in time. So we do always need to measure time. So we'd record time and volume of gas produced, or time and the loss of mass. We would then be able to plot a graph of time versus either the volume of gas or the loss of mass on the y-axis, and those 2 would stand in place of the change in concentration. And what this would look like would be looking like this graph on the next page, on page 11. So we have time along the bottom and our volume of carbon dioxide being produced. Notice that after a while it reaches a plateau. At this point we say it's reached equilibrium. So in kinetics we're only really interested in this first part of the graph, how quickly it takes to reach this status quo, this equilibrium position. In the other packs we're going to be studying this term equilibria. We're more interested in where we end up in terms of the position of equilibria. So if I then plot on this graph the values from each of the tables below. So we know 1, we know what our curve looked like for 1. So for 2 and 4 we're going to end up in the same place. But for 3 and 5, we're going to end up with half the volume of carbon dioxide that we did in 1, because I've got half the number of moles of hydrochloric acid. Likewise, for 6 and 7, I'm going to end up with double the amount of carbon dioxide. So once I've plotted everything on my chart, I should get something that looks like this. So we're now looking at pages 12 and 13, and this is where you're going to need your textbook. So what we'd like you to do at this point is pause the video and go through the next 2 pages, drawing in an example, a diagram and a method for these methods of measuring the rate of a reaction, starting with titration and measuring the volume of a gas. So going through this first example, sampling, quenching and titration. Now this is one of the most commonly used methods, but you do need to get the steps and certain parts correct. So we have our reaction, which we're going to do. In this case, I'm going to do an iodine-propanone reaction. It's one we're going to study in the next topic. But this works very well for any reaction that either produces or uses hydrogen ions or OH negative ions. In this example, my hydrogen ions are acting as a catalyst. So what I'm going to do is remove samples of a known volume using a pipette at repeated time intervals. Again, remember, we have to include some sort of time measurement if we're dealing with rates of reaction. Now we need to quench the reaction. In other words, we need to stop the reaction at this point. Now the easiest way to do that is to remove the catalyst. Remember, catalyst speeds up the rate of the reaction. So if the catalyst is removed, the speed of the reaction will drop, and basically that will freeze the reaction at this point. So we can place on ice and just get it cold, or a better method, especially if we're using acid, is to add sodium hydrogen carbonate or sodium carbonate to remove the acid catalyst. We never use sodium hydroxide. The reason for this is the OH negative ion here is a very strong nucleophile. So it's likely to either do nucleophilic substitution reactions or to hydrolyze things, whereas the carbonate and hydrogen carbonate ions can't do that. Once we quench the reaction, we would then titrate it against, in our case, thiosulfate or silver ions. But basically you can titrate it at this point to work out what you have left over, and that'll give you an idea about the rate of the reaction. The second method is also widely used, and any time you have a gas being produced, it's probably going to be your first choice. So you have some sort of reaction going on in a sealed container, and you're collecting the gas in your gas tube. So you're either going to use a gas syringe or a data logger, as we did in the experiment, or we will do later on in our experiment. And again, you're going to plot volumes versus time. So I need the volume of gas and I need the time. We take the tangent and that gives us the rate. We then can repeat our experiments with different concentrations and again measure the volume and the time taken. Recording the changes in mass is the same as the one we talked about on the previous page, where we have, again, this is used for the loss of mass as a gas escapes. It's usually not as widely used as the gas syringe method, but it's still a method you need to be aware of. So number 4 on our list is a measurement of a colour change. We call it colorimetry. This works with any reaction where there is a colour change. For example, in this reaction we're going from the brown iodine to the colourless iodide, so we can measure the colour change there. Here we're going from bromine to bromide, again another colour change. So we have our light source, our filter, our reaction mixture, our light sensitive units. We use a data logger for this, so these two parts are combined. And again, we can look at the rate of change of colour. And because the intensity of the colour is directly proportional to the transmission, via something called Beer-Lambert's law, we can work out the change in concentration. Number 5 is the least likely to come up. This is measurement of IR absorption. It tends not to be a practical but more something that comes up under mass spec and IR. So you'd be looking for specific wave numbers which change during the reaction, and you'd need to look at the data book. However, measurement of conductivity can be used for any reaction which produces or uses up ions, resulting in a change in number of the ions. And basically what you'll be looking at is how the conductivity changes through the reaction. We tend to use a conductivity meter for this. It's very similar to a pH meter, which you could also measure the rate of the reaction. So we're on page 14 of your notes, and we're looking at the change to the rate during a reaction. And you can see there that the reactants A and B, their concentration decreases with time until you reach the equilibrium position. But the product C increases with time. Now, the steeper the curve, the faster the rate of the reaction. And the reaction is the quickest at the start because here A and B are at the highest concentrations, so they've got the most frequent collisions. But after a time, the reaction starts to slow down as there are fewer reactant particles to collide, until we reach a position of dynamic equilibrium. We can measure the rate of the reaction by taking a tangent to the curve at different times and measuring the gradient. If you remember, the rate of the reaction is equal to change in concentration, which is the change in my y-axis, divided by the change in time, which is my x-axis. At the start of the reaction, known as the initial rate, this is the point at which we know the concentrations with the highest degree of accuracy, because they're simply the starting concentrations. So in the next video, we're going to be looking at this method called the initial rate method for determining the rate of a reaction.